I do work on many aspects of cosmology, including things on the scale of the whole universe. But today I'm going to focus a little bit closer to home, and I'm going to primarily talk about the Milky Way and understanding the cosmological context of the Milky Way. And I have to admit, I'm a little bit nervous because I know that there's a lot of people in the audience who know more about the Milky Way than I do. But I do think I understand something about how the Milky Way fits in to the broader picture. And that's what I want to kind of talk about today. So, I mean, I think it's just incredibly exciting what we are learning about our galaxy and how we can use our galaxy and the very nearby universe to learn about really fundamental questions in both galaxy formation and fundamental physics, like the nature of dark matter. So I'm going to kind of try to give these hints of how we can use our galaxy to learn about what dark matter is, how galaxies start forming, and also about the assembly history of the Milky Way itself. So I'm going to be talking about work done with a large number of people, of my current and former students and postdocs. These people in yellow are all people who are either current, mostly current, a few former, and then especially talking about the work of two of my former students, Ethan Nadler and Yayuan Mao. But also the work of big collaborations, including the Dark Energy Survey collaboration, especially the Milky Way Working Group, the SAGA collaboration, and my collaborator Marla here, who's been an amazing partner in that work. I'll also mention work from the DESI collaboration, and then some work that I've done with wonderful groups of dark matter theorists who have helped us understand how this connects to the fundamental physics side. Okay, so just to start at the beginning, you all know that we have this kind of interesting lambda CDM picture. And today I'm going to mostly focus on that red 25%, the dark matter. We don't know what this dark matter is. Nice kind of plot about our ignorance from Tim Tate here, kind of showing the landscape of possible models that the dark matter particle could be. So we want to understand what particle it is it truly cold? And in the sort of more structure formation flavor of that question, we want to understand, is there any indication that cold dark matter doesn't work and doesn't work on small scales? Can we detect any sign of less or even potentially of more substructure than we would predict from cold dark matter? Or can we detect any interactions between dark matter and anything else, including self-interactions or interactions between baryons and dark matter? So this very simple but confusing model actually makes very concrete predictions, and that's what I've spent a lot of the last 20 years doing, trying to figure out what kinds of predictions in detail does CDM make. And this movie just shows two example universes which happen to have different amounts of dark matter. And you can see that, different changing the amount of dark matter, changing how it clusters, or potentially actually changing the nature of dark matter results in different amounts of structure formation. And that is the case on a wide range of scales. And those predictions are by now really, really detailed. We can do high resolution cosmological simulations on a really wide range of scales. And this is just a handful of the kinds of predictions you get out of CDM. You get predictions for the numbers and clustering of dark matter halos, features in the dark matter clustering, like this transition between the 1 and 2 halo term. You get a very robust prediction of hierarchical merging that tells you that there's lots of substructure and substructures within substructures, and also destroyed substructures that give you streams. And we know something about the shapes of these profiles. And these predictions are really well tested by now on large scales, but they're much less well tested on small scales. And there's lots of different things that could, in principle, happen on small scales. So when we ask this question, is the dark matter cold dark matter, from the structure formation point of view, CDM is always an approximation, okay? But the approximation that we're making when we talk about CDM in the context of structure formation, it's basically that the free streaming length of the particle is small enough not to impact structure formation on any measurable scale, and also that any interactions that may exist between dark matter and normal matter, or between dark matter and itself, don't impact structure formation. So when I say CDM, that's what I mean. But there are many alternatives to CDM that do one of these things. And in particular, there are alternatives that suppress power on small scales and also have an impact on galaxy formation. And examples of those include warm dark matter, which suppresses the number of dark matter halos, fuzzy dark matter, ultralight scalar dark matter, self-interacting dark matter, which actually changes the density profiles, late decaying dark matter, which also results in fewer substructures. So these are just examples of what different kinds of alternatives to CDM can do. They can look identical on large scales, but different on small scales. And just to put that in a cosmologist framing, we can talk about the dark matter power spectrum. This is essentially the clustering as a function of wave number from large scales here on the left and small scales on the right. And the basic idea here is that, this part of the curve is very, very well measured from large cosmology surveys, some of which I have worked on, and many people in the room I know have also worked on some of these, including CMB, but also galaxy surveys in the local universe, which are starting to probe here. But when we look very nearby in the local group, we can actually start to get a handle on very small scales, which potentially can start to probe all of these interesting models.
Risa, can I interrupt for a second?
Yeah.
When I was a kid, I learned that C in cold dark matter meant that the dark matter was non-relativistic at decoupling or something like that. Is that identical to what you said on the previous slide, which was about
it's basically identical to that.
And is that a coincidence, or is there some fundamental reason that non-relativistic decoupling is the same as you don't impact structure formation? And if the answer to that is hard, feel free to tell me. You'll talk about it later.
I think the answer is yes, that is equivalent, and let's talk about it over a glass of wine. Yeah. Okay, so this is, of course, not quite as simple as you might like, because there are also baryons in the universe that disrupt what you might see in just pure dark matter simulations, and in particular, galaxy formation processes can also impact the galaxy population within dark matter halos. And this is just a few examples. Reionization can suppress, can mean that some galaxies never form in certain halos. Feedback can change the number of objects that you have or their masses. And in a galaxy like the Milky Way, the central galaxy itself can disrupt a lot of the substructures in a way that you wouldn't have if you had that impact of the central galaxy. So it's important to keep all of these processes in mind when we talk about the comparison between galaxies and dark matter halos. Now, as Hogg said, galaxies are, a lot of what I have done over the course of my career is try to understand the connection between galaxies and dark matter halos on all scales, and what we can learn from that. And the basic idea, right, of the model that we have is that galaxies live in dark matter halos. Every galaxy, every halo above a certain mass probably forms a galaxy, and their masses are pretty well correlated. So we can make really detailed predictions for the dark matter halos, and we can assume that in every clump of dark matter there is a galaxy, with that some sort of an approximation. And by doing that, we can use the galaxies as dark matter tracers. So this is a plot from a review article I wrote with Jeremy Tinker a few years ago that looks at the fraction. So as a function of halo mass, the fraction of that total dark matter that turns into stars. And the basic point here is that this is very well determined from lots and lots of different measurements for relatively massive halos, say above 10 to the 11 or 10 to the 12, very well understood and relatively well measured. But there's until recently very few constraints for lower mass systems. And so today I'm going to be talking mostly about this part of the plot, where you can see in 2018 I was not bold enough to extend these lines, but now I'm going to be bold enough. But the basic thing we're trying to answer, including down to this really small halo mass regime, is how much scatter is there between the galaxy properties and the halo properties? Is there some halo mass here below which galaxies just never form? So what is the threshold of galaxy formation? And also, do all halos survive baryon processes? So those are still questions that are really kind of open questions on this low mass end. And what I'm going to be talking about today is essentially, what can observations of the very smallest galaxies that exist teach us about that small scale power and consequently about the nature of dark matter? How and in what halos do the smallest galaxies form? And then I want to understand, because some of these measurements we can only make in the Milky Way, we also want to understand, how does the Milky Way compare to similar galaxies? So how does the formation history of galaxies like the Milky Way impact their satellite populations? And how do measurements of the specific satellites and stellar halo and streams in the Milky Way inform our understanding of its formation history? And then consequently, how that fits into the broader cosmological context. So now I'll go to the Milky Way itself. Probably most of you have seen this just gorgeous picture of the Milky Way from Gaia. Maybe we're going to get an even better picture in 2 weeks.
Actually, whenever Gaia shows up, they say it's not a picture, it's a histogram.
It's a histogram. Yeah. So, I mean, yeah, which is amazing, which is just amazing, right? Each one of these is a star. But the thing I want you to focus on in this version is that there are these two galaxies here that you can see besides the Milky Way, the Magellanic Clouds. And most of you probably know that there's not just two of these. There's actually something like 60 of these so far that we know of, which are all smaller than the Magellanic Clouds, which have been discovered over the last 20 years or so in a series of surveys, starting work led even by your famous director here and Beth Willman with the Sloan Digital Sky Survey. We found a whole bunch of them with the Dark Energy Survey. We found about 20 of them. And so we're up to a number of about 60 of these satellite galaxies that are, that are systems that are actually orbiting our own Milky Way in the dark matter halo of the Milky Way and gravitationally bound to it. And the masses of these things have a huge range, all the way from the largest system, the LMC, which is about 1/10 the mass of the Milky Way, all the way down to these really tiny ones like Segue 1, which have just a few hundred stars. Okay, so a couple of years ago now, we did what I think is really the first comprehensive most of the sky survey of these things to really try to understand not just detecting these things, but understanding their selection function. And so this is a search of about 3/4 of the sky using the Dark Energy Survey year 3 data, which is in this outline in red, and the Pan-STARRS data, which gets you down over about 3/4 of the sky. And all of these dots are satellite galaxies that have been detected. And you can see here that just by eye, you can see, so here's the LMC, here's the SMC. DES detected a whole bunch of systems here, which were kind of, relatively nearby the Magellanic Clouds, and in fact, kind of more than you might have initially expected, which is one of the interesting things that that'll talk about in a second. So what I want to ask is, what do these data tell us about the halo population of the Milky Way satellites? And in order to do this, we basically take some realistic simulations of Milky Way-like galaxies. So these are simulations that are re-simulated from a large cosmological volume, and they're chosen to be Milky Way analogs. I'll say a little bit more about what that means in a minute. We then paint on galaxies using a statistical model for the connection between galaxies and dark matter halos. That model includes the impact of baryons from the disk as one of the modeling parameters, and includes scatter, several other things. We then observe those fake, those model halos, just like the data is observed. So we apply the selection function based on the imaging data, and then calculate the likelihood of the model, given these parameters. And so it's really joint modeling of the formation history of these systems, the cosmological context, the observational selection function, and joint modeling of the dark matter halo population and the galaxy halo connection. So I said we looked at Milky Way analogs. This is an important piece of this work, and it turns out that you can't actually model the actual Milky Way systems unless you have systems that have merger histories like the Milky Way. We tried to do this with just typical 10 to the 12 solar mass halos, and we were unable to do that, and I'll say more about that in a minute. But when I say Milky Way analogs, what I mean is things that are consistent with the mass and concentration of the Milky Way, so about 10 to the 12 and concentrations of about 10, and had two important merger pieces of their merger history. The first is a recently accreted large Magellanic Cloud. We think the Magellanic Cloud was accreted within the last few gigayears, 2 gigayears or so, and that was quite an important event. And also, somewhere between 5 and 10 gigayears ago, there was another major merger event, which is now called Gaia Enceladus. In the analysis I'll talk to you about, we had two of these systems. I'm really excited about this work we've been doing with Ethan Nadler and an undergrad at Stanford, what we're calling the Milky Way-ist simulation suite. So we now have 25 of these systems, which are selected from a cosmological box. These are, each simulated with particles that are a few times 10 to the 5 solar masses, so a few million particles in each halo. And so we now have a range of masses and concentrations and formation histories, but that we think are all consistent with what we know about the mass, concentration, and LMC and Gaia Enceladus of our system. And I think this is a really exciting simulation suite that we're going to be able to do lots of things with.
So in every one of those pictures, I should see an LMC.
Yes, there is.
I mean, it is believable.
So I'm just going to show you one movie here of one of them, where I highlighted the Gaia Enceladus and the LMC, and then we can stare at those individual 25 systems later if you want. But this is just a nice movie of these things actually merging in. I believe that this one is the LMC. So that's the Gaia Enceladus. Oh, maybe that one was the LMC. Yeah, I tracked it wrong, but yeah. Okay, so we've got 25 of these, which is pretty cool. Okay, so we do that analysis. What do we find? Well, the first thing, some of you might have heard about this thing called the missing satellite problem. There's no missing satellite problem. So what I mean by saying there's no missing satellite problem is we are able to predict, we have reasonable models that get the right number of satellites. And that is because some of the low mass halos do not light up, which we kind of expect. So we have a model, which is an excellent fit to the data. But that thing that I told you is that actually matching the distribution on the sky requires the presence of an LMC-like galaxy and its satellites. So if you try to match the data with a regular 10 to the 12 solar mass system that did not have a recently accreted LMC, you can't get the distribution on the sky. You can't basically reproduce the fact that there's more satellites around the LMC than there are away from the LMC. So in the context of this model, there's 60 that are detected, but we predict about 220 total, about 25 of which are actually associated with the LMC. And that's a kind of higher number than you might have naively expected, but that's because the LMC is accreted relatively recently. And some of the other ones that may have come in earlier have already been destroyed. So, we should get another 150 or so.
Risa, if you had done this analysis like 4 years ago without the southern sky, would you have matched the northern satellites without without having to worry about analysis.
Yes, we could have done it. We could have matched just the northern ones without the LMC, and we would have gotten the galaxy halo connection slightly wrong. Yeah. And so I think it's important that we now have 3/4 of the sky. Yeah. So yeah. Yeah. Okay, so what does this tell us about the threshold of galaxy formation? So I told you that, maybe those very low mass things don't light up. But I think we have a really interesting constraint already, which is that it seems that the faintest systems that we have already detected, remember, these are very faint, just a few hundred stars, they live in halos that are around a few times 10 to the 8 solar masses or less. Okay, so the basic point is that there's already so many systems detected that you have to put them in halos that are as low mass as a few times 10 to the 8. There just aren't enough more massive halos for them to exist. So that's already an interesting number, right? So this is the stellar mass as a function of halo mass. This is the peak mass that the halo ever had before it started getting stripped by its host. Okay, and this plot, F-gal, this is saying when this is 1, this is saying that every halo of this mass hosts a galaxy. And when it's 0, it says that no halo of this mass hosts a galaxy. You can see at 10 to the 7, the error bar is essentially as large as it might be, right? So I don't know anything about whether galaxy formation turns off or not at 10 to the 7. But what I can say is that about half of the galaxies at 10 to the 8 are already hosting a galaxy. And I think that's already a really interesting number. And this is something that I'm thinking about a lot right now. And I don't have any more specific answers than what I already told you, but I just want to speculate for 1 minute. So first, just to restate that, these results are implying that at least half of current Milky Way subhalos that started at 10 to the 8 host observable galaxies. They're very small observable galaxies. And, it's hard to form stars at this mass after reionization, although there's still some controversy about this fact among the experts. And there's not a lot of time for them to form many stars before reionization. So the basic thing I want you to take away is that we're actually pretty close to detecting what I think is the real threshold of galaxy formation. And I think it's probably not that far below 10 to the 8. And I think that's really interesting. So roughly half of today's existing 10 to the 8 solar mass halos were more massive than 10 to the 7 before reionization. So maybe they had enough time, to form those galaxies in that short period. But I think, this is already interesting and going to get more interesting as these results tighten a little bit. Okay, so now I want to move on to ask, what does this tell us about dark matter? Okay, so just to get back to this power spectrum, the basic idea is that if dark matter is not cold, if it, for example, is warm, if there's if there's a warm dark matter which has a large velocity dispersion, those particles will free stream out of the halo and they will suppress the small scale structure. Okay, so if we actually detect that structure, it can rule out, these fast moving particles. Okay, so I mentioned that we kind of jointly constrain the dark matter physics and the galaxy halo connection. So we have in the model that I told you about, a full model for the galaxy halo connection, which includes, what the disk might do. It includes scatter in the galaxy halo connection. It includes the faint end slope. And these things are actually reasonably well constrained. So this galaxy disruption, we find that, so some of you who pay attention to this field might know that, these fire simulations have indicated that, some satellites are disrupted. We're consistent with what they predict, but, with some error bar. But the main thing that's new here is that we actually, we can constrain the mass scale of possible suppression due to dark matter physics. And we basically have an upper limit on that. That's a few times 10 to the 7. And I want to say a little bit more about that in now maybe more understandable terms. So So again, we're fitting the Milky Way satellite population with a model that has some suppression to the subhalo mass function, and then marginalizing over the galaxy halo connection and the properties of the Milky Way halo itself. Okay, and so this middle plot here, so the basic idea here is that different kinds of dark matter models would suppress the power at large K. Another way to think about that is they suppress the number of dark matter subhalos above a current mass, and this is just 3 example models. And the bottom line of our results are that we find that the current satellite observations are sensitive to about a 25% suppression in the subhalo abundance compared to CDM at a few times 10 to the 8. So to say that in slightly different words, it means that whatever physics might or might not be changing the subhalo mass function, it can't be suppressing the subhalo mass function at a few times 10 to the 8 by more than about 25%. Okay, so that's actually a really strong constraint, and it's a strong constraint on a really wide range of models. So this is kind of a summary of some of the models we've looked at from this PRL paper last year, and I'll kind of talk through each of these models briefly. But the bottom line is, we really get quite strong constraints on a really wide range of models, and it's important to note that these are just example models that have a specific thing, and really we're making a generic statement that any model that suppresses power can have almost no impact at 10 to the 9 and not more than 25% at a few times 10 to the 8. Okay, and this is really cool because the physics that we're probing here is really just a few months after the Big Bang. That's what when these where that comes into the power spectrum. So the bottom line is that if we have a thermal relic warm dark matter model, the limit on the mass of the warm dark matter model is 6.5 keV at 95% confidence. So that's comparable to limits from the Lyman alpha forest and strong lensing. Very different assumptions about the systematics, and I'd be interested to chat more about this. So just to kind of very briefly go through a few of the specifics here. The basic idea in warm dark matter is the dark matter, because these halos exist, the dark matter free streaming length must be smaller than the halos that host the ultra-faint dwarfs. Okay, so that has to be smaller than about 10 kpc. And one consequence of that is people have talked about an interesting possible model for warm dark matter, which is sterile neutrino dark matter that could produce a 3.5 keV line in the X-ray. That's now basically entirely ruled out. So that model would be here, and our model rules out everything to the left of that red line. So very hard for this to be dark matter and be consistent with these Milky Way results.
And to pull that back to the observations, if that model were correct, you would say that DESI wouldn't have found that collection of
DES, yeah.
Sorry,
DES would not have found that many systems. That's right. That's right. Okay, you could have a dark matter model where dark matter and baryons interact with each other. And what can happen in such a model is that there's collisional damping due to scattering between dark matter and baryons at early times, and that also suppresses power at small scales. And in this plot, this green line is previous constraints from the cosmic microwave background, which can also independently constrain these models. But it turns out that the satellites are actually about a factor of 1,000 more constraining than the CMB. So that's really, really cool. We have another result that shows that you can constrain velocity dependent dark matter proton scattering. But it's really cool because these models really kind of map almost exactly onto warm dark matter models. So that's just convenient phenomenologically that we can really essentially, it's not exact. You can see one of the models is this dashed line and one of the models is the solid line, but almost exactly in terms of the K dependence of their suppression. We can also distinguish from fuzzy dark matter. So if the basic idea here, again, is that you can have a fuzzy dark matter model with it's it's like an axion-like model. So the QCD axion is over here. You can have a mass which is quite a bit smaller than the QCD axion, which makes kind of fuzzy wave-like dark matter. And the basic idea is that the de Broglie wavelength of such a dark matter model must be smaller than the sizes of these dwarfs. And so that can be interpreted as a lower limit on the ultralight axion mass in this case. One thing that's interesting is that, so here, the models I just told you about were just about the number. There are some ways to distinguish the spatial distribution, and so the suppression of the subhalo mass function and the radial dependence. And this is just an example from a recent paper where we looked at cold dark matter, self-interacting dark matter, warm dark matter. So this is cold dark matter where it's dark matter only without a disk, and this is cold dark matter where you have a disk that destroys some of the satellites. And the basic point is that there actually are different features that happen in these three different models in terms of the mass dependence, the radial dependence, and what happens with this LMC situation, right? So the self-interacting dark matter model, for example, doesn't have the same kind of suppression because the satellites get pre-processed through the self-interactions in the LMC, and so there's fewer of them that would come in as LMC satellites, okay? So the basic point to take away here is that as these measurements get better, we may actually be able to distinguish between these different kinds of models that have different effects. One last model that I want to mention that can be constrained is a model where you have some late time dark matter physics, like decaying dark matter that happens at relatively late times. And there have been proposed models where dark matter lifetimes are relatively short that could help alleviate the Hubble tension and if you've heard of the sigma 8 tension. Many of these models are disfavored. So this X hashed region here, which are relatively short dark matter lifetimes, those short dark matter lifetimes, which would actually also suppress subhalo abundances at late times. And so those are also ruled out. It's the same measurement, same constraint on the.
How does dark matter goes to dark photons?
Yeah. Okay, so Milky Way satellites aren't the only way to detect small halos. Another way is strong lensing, and I'm only going to very briefly touch on this. This is an example of a detection of a substructure with ALMA, and basic idea here is you can detect substructures. You can detect individual substructures at about 10 to the 9. And there's really three kinds of analyses that one could imagine that can get sort of similar sensitivity to Milky Way satellites: the Lyman alpha forest, strong lensing, and stellar streams. I think it's exciting for the future to think about combining these probes. And this is one example. We combined strong lensing analysis with the same Milky Way satellite analysis that I told you about. And the constraint on warm dark matter goes from 6.5 in the Milky Way satellite case alone to 9.7 keV when we combine these. And so I like this plot that was recently made by Alex Wagner, sort of constraints on warm dark matter model as a function of publication year. And so this is that combined constraint. Basically, you break some internal degeneracies in the modeling. But the strong lensing constraints are also going to get a lot better soon. I'm not going to talk about this, but there's a great paper by my student, Sebastian Wagner-Carrena, about how we can actually model about 100 gravitational lenses at once. And you know, we haven't done that on data yet, but we will be doing that soon. And I think it's really exciting. Okay, so far, before I move on, you know, the Milky Way satellites indicate that there's very little suppression of small scale power compared to the CDM prediction, and that provides strong constraints on a wide range of models. The Milky Way satellites that we know of also indicate, I think, that we're getting close to identifying the threshold of galaxy formation. So in order to push this further, what can we do? Well, first, we can identify more satellite galaxies, probably about 150 more. Actually, on the flight over here, I learned about 7 more that we think have been detected, which is really exciting, in that white area that just hadn't been looked at yet. So that's great. We can combine more with other probes of small scale structure. There's lots we can do to improve our simulations and modeling. And we can work to put the Milky Way into cosmological context, both observationally and theoretically. And I'm going to spend most of the rest of my time on that topic. So many things we can only measure in the Milky Way, like some of the things I just told you about, dimmest satellites and streams, the local dark matter distribution, resolved star formation history. So it's really important to put the Milky Way into context, both observationally and theoretically, and ask also whether that modifies or strengthens any of the dark matter conclusions. So we've been working on an observational project to do this for many years with Marla Jiha, who's here, and Yaoyuan Mao, called the SAGA survey. SAGA stands for Satellites Around Galactic Analogs. And our goal initially was to measure satellites to about 100 systems that were like the Milky Way. And when we came up with this crazy goal, it seemed almost impossible. And I'm really excited to tell you that we have now done this. So we have 100 systems that are basically L-star-ish galaxies. They are all over the sky. Okay, so we're using existing imaging surveys, so that includes the DECAL survey and the DES survey at this time. To give you some context, right, in the local group, I told you that we have about 60 satellites in the Milky Way, about 25 satellites in M31. The Sloan survey, which goes out to about 200 megaparsecs, gets on average about 1 satellite per Milky Way host. And there's recent, quite complementary work that just came out in the last year or two, Jenny Green, Scott Carlston, which uses tip of the red giant branch and surface brightness fluctuations that can go out to about 20 megaparsecs. And we are kind of in this intermediate regime, 20 to 40 megaparsecs, where we're trying to get 3 to 4 satellites per host galaxy. Okay, so we're not getting down to the ultra faint regime, but we can actually get a statistically interesting sample. So this is a hard observational project because in the virial radius of the Milky Way, which is about a square degree at this range of redshifts, there's a few thousand galaxies. And so we're looking for 4-ish out of the few thousand. And so in the first stage of this project, we just brute forced it and got redshifts for about, you can cut it down to about 1,000 and be pretty confident. We actually got several thousand for 8 systems in stage 1, and then for 36 systems, we improved our cuts so that we could do this with about 1 pointing on the key telescopes AT and MMT. And Marla has then heroically followed up all of the loose ends with Palomar and several other surveys.
It's too bad we're wearing masks because you can't see me just like loving how insane this project is.
It was totally insane.
That is insane.
It was totally insane. Let me tell you, it was long and painful and really, really, really fun. Really, really fun. So we've done this. We have published results on 36 systems. This is what they look like. You can see that they have everywhere from 1 to 10 systems that we've identified. That's going down roughly to -12 in R-band magnitude. Okay, sorry, it's actually 0. Two of the systems have 0 satellites, and one of the systems has I think had 9. These are the 36 hosts, so the colors correspond to 1 host per thing. And this is really awesome to already have 36. It really starts to allow us to understand host-to-host scatter, counting the number of systems. One thing, so here on the upper left, we're showing the luminosity functions. Each color corresponds to 1 host system. So you can see a few of them have 0. The Milky Way is here, kind of right in the middle. And you can see also that there's a correlation between the brightest satellite and the overall normalization of the luminosity function. So if you have one bright satellite, you also have more satellites overall. And that is actually what you should expect from CDM. That should be a function of the host halo mass, but also the formation history of the system. And so we've now really detected that correlation quite convincingly. We also can say something about the star formation of satellites. So this is a plot of the quenched fraction as a function of the stellar mass of the satellites. So here is what the systems look like in Milky Way and M31. So the first really surprising thing is that we found a whole bunch of star-forming satellites in these systems, and more than we might have expected. So the overall quenched fraction is there's more star formation than there is in the local group. We now have 100 systems, so this is preliminary. We still wouldn't trust the error bars yet, but this is from 100 systems from the Saga data, and we're still getting sort of more star-forming satellites than you see in the Milky Way. And but there is a big scatter. There is a big scatter. So the fact that the Milky Way is somewhere in this distribution of 100 is not shocking, but quite interesting. This is just a preliminary plot of the star formation rate as a function of stellar mass of I think about 370 satellites. This is hot off Marla's computer from yesterday. So really excited about the kind of science that we can do with this many systems. So as I said, we now have 100 Milky Ways. We expect to publish results on these 100 in roughly this fall. So I think we have 368 satellites total that we've identified. About 220 of them are newly discovered. And we were not very efficient. The reason David said that this was a crazy project is that we had to get about 45,000 redshifts in order to identify these 300 systems, because we really wanted to understand our completeness. That was a really key part. And more than half of our redshifts are outside our main target region at all to really validate our completeness.
And you took all 46,000 of those redshifts and you threw them in the garbage.
We still have them.
Do you think they'd be useful?
Yes, I do think they're useful. They're useful for all kinds of things, and we'd be happy to talk to you about some of the ways that they could be used. So I'm just really in love with this plot. You can see that 6 of our systems out of 100 have no satellites down to this limit, and some of them have 10. So it's a big scatter. And so if you just have one of these, you can imagine that it's hard to really figure out what's going on. So we can do a lot more. One of the things you can do is so really we have more low redshift galaxies than any other survey had before, and this is really exciting. So one of the things you can do is use these data to effectively train algorithms to detect low redshift galaxies, and we have 2 methods of doing that. One is just very conservative color cuts, color and surface brightness cuts. We also have a CNN that we train to do this really efficiently, and it works really well, especially below redshift 0.03. Basically, there's information in the images. Most of these galaxies are low surface brightness. They look like fuzzy blobs. If you actually use the image itself, you can tell. Before we had this nice CNN, we had the Risa neural net. I literally looked at thousands and thousands of these, and I got very good at identifying them. But this is probably better. I'm also really excited about some stuff that we're doing with the DESI survey. So to take a step back, DESI survey is a new spectrograph. It's been observing now. The first anniversary of it of the survey was a week ago. In its first year, DESI has taken about 16 million spectra. It's truly incredible. 12.5 million extragalactic redshifts and another 3.5 million Milky Way stars. And once you have numbers like 16 million, you can put in just few spare fibers on each thing and get a whole bunch of things. So I put in a proposal for a secondary target program to really focus on these very low redshift galaxies. We use the Saga data as a training set to figure out how to detect these things. So we're looking for galaxies from -19 to 21, similar to Saga, and really trying to optimize getting as many galaxies at redshift less than 0.03 as we possibly can. There's a bright galaxy survey that is targeting galaxies mostly down to 19.5 and a little bit down to 20.3. It's already a third done in the first year. DESI is working even better than we expected. The throughput is amazing. They brought down the time per pointing, like it's just incredible. So, and our technique is working really well. So we have a technique with the CNN, which gets us a sample that peaks at about 0.1. And we really think we're missing very little, very few of the galaxies at very low redshift. And so if we were actually able to get all of the fibers that we want, we would be able to get a sample of basically a complete sample of 10 to the 8 solar mass galaxies out to redshift 0.05. But we already have 20,000 dwarf galaxies. So 20,000 galaxies with stellar masses less than 10 to the 9 from DESI. And that's in 1 year. So really, really exciting. So lots of things we can do with that. I maybe have a few minutes left. I'll just say a little bit about some of the new modeling that we're doing, and I'd love to talk with anyone more about this. So I mentioned, so there's 2 suites of targeted zoom-in simulations that we're doing. One is the really Milky Way tuned ones that I mentioned, and the other is a suite of simulations that spans a really large mass range. So we go all the way from the LMC up to 10 to the 15 solar mass clusters. Actually, 2 of these samples were previous PhD theses in my group, but we've now fleshed out the whole mass range. And so I think this is really exciting because what it enables us to do is track the merger histories and the subhalos that build up all of these galaxies. So it really is essentially, if we go from the dwarf satellites that come to build up the LMC up to the 10 to the 15 solar mass halos, it really is the full range of observed galaxy masses, and it really complements this Milky Way suite. So one of the things that we can do with that is to really track star formation histories in these systems. And my student Richie Wang has done something called Universe Machine. That's a model I developed with Peter Baruzzi, where the basic idea, as you heard, I really like simple models. So the basic idea is you just say the star formation history of a galaxy over its whole history is related pretty closely to the mass accretion history of the dark matter that comes in. And you have a parameterized form that you then constrain with all available data. So this has been constrained basically with the star formation rates and stellar mass functions of galaxies from redshift 8 to the present. But what we can do now, which is a new technical thing that was quite challenging, was combine that with zoom-in simulations so that we can really model the full range of things. And so with this set of simulations, so this is now stellar mass versus the peak subhalo mass over this entire range, all the way from the things that are barely hosting galaxies up to cluster mass systems. And one thing that's fun that you can look at here, so what we're able to do that wasn't possible before is really track the full histories all the way back to the point where the galaxies start forming. And the dashed lines in this plot are the mass accretion histories. The solid lines are the stellar mass buildup. So you can see that the LMC builds up its stellar mass late, even though its halo forms early. The massive galaxy, you can trace these things back all the way beyond redshift 8, which is really, really cool. Yeah, so we can ask about how the smallest galaxies form, right? We can get really detailed predictions for dwarf galaxy star formation histories. In the previous modeling, this was really unconstrained at low mass. So the modeling needs improvement in this regime. And I'm really excited that the Saga data that I told you about will be able to constrain this along with resolved star formation histories from the local group, now that we really have the mass accretion histories for the corresponding systems in the local group. So one of the things, we have these new targeted zoom in simulations. We can actually trace the star formation histories. And we're also working on tracking resolved star formation histories, like actually labeling each dark matter particle with a stellar mass to study the impact of different merger histories. And I think this will be really interesting to do in the context of those Milky Way-like simulations to really try to understand this. And we have just one hint of a result that's new work. So Phil Mansfield is the person who's working on the star formation modeling, and Elise is working on the observational implications for this. So this is an example of 4 halo histories. So 4, resolved systems, and looking at what fraction of the halo mass on these 4 plots and the stellar mass on these 4 plots came in different merging events. So the basic thing I want you to take away here is that, even when you have, a Gaia Enceladus and an LMC coming in, lots of things can happen. And if we want to understand our Milky Way specifically, we have beautiful information coming from Gaia and from other surveys like DES and DESI and soon to be Rubin LSST. Understanding the context and what the individual merger histories do is going to be really, really important. And so I'm really excited about what we can do with this set of simulations. So I'll just end with a few summaries here. So first of all, we've really now mapped most of the sky. Not quite. We've mapped about 3/4 of the sky, but we haven't mapped it all the way out to the virial radius of the Milky Way. So there's still lots more to find. I would say at least 150 more to find. And even though we don't expect those things to be smaller, when we find more of those things that are at the limit, it will put much stronger constraints on the dark matter models. And already the lack of a cutoff is really yielding stringent constraints on both the galaxy halo connection and dark matter physics. I think, it's really exciting that I think in the next decade, we will definitely either detect the threshold of galaxy formation, or we will detect some deviation from CDM, or possibly both. And I think either of those is really, really exciting. So it's really, really cool. I think the Saga survey really helps put the Milky Way into context by looking at these satellite populations of 100 systems, and detailed modeling of Milky Way-like systems and a broader set of Milky Way mass systems can really highlight the extent to which the accretion history of massive satellites matters. So I think this is a really exciting future. We have real potential to detect deviations from CDM or really put limits on a wide range of models that would be different. I think we can do a lot when we combine constraints, either from getting more satellites, combining with other probes of small scale structure. And I think there's a lot we can do with new modeling to really connect our understanding of the formation history to the satellite statistics and dynamics. So I will end there, and I'm just going to put up one more slide of things that I didn't talk about. I'm not going to talk through this, but just in case you want to ask me about any cosmology topics in the next few days when I'm here. Thanks.
So I'm sure people have questions. We will take questions. Before we take questions, because I just want to mention that Risa is going to be here tomorrow and on Tuesday. So there'll be opportunities to chat with Risa, and her schedule is being managed by Risa. So right directly to Risa. Let's take questions.
Solar mass halos, what fraction of the stars are surviving from before reionization?
I think at that limit, almost all of them. Yeah, so I think in the smallest halos, I think all of the stars form before reionization, most likely. I mean, that's my best guess. I think that's consistent with the data. I don't think that the data convincingly shows that, but I think it's consistent with the data. Do you agree? Yeah.
Greg Bryan has a question online.
Hey, hi, Risa. Thanks.
Hey,
This is
Greg.
beautiful talk. I really liked it.
Thank you.
I have a concern and a question, and I'm not sure
Great.
what order I'm asking them. So actually, following on that last question about this lower level, this lower mass cutoff for star formation,
Yeah.
my concern is phrasing it in terms of a mass, because for those of us who are really interested in what controls star formation in the lowest mass halos, one of the guiding things is the depth of the potential well, which is really
Yes.
characterized better by the virial temperature.
Yes.
And so I guess my question is, why are you phrasing this M peak in terms of a mass and not something, I mean, it's really this virial temperature probably is a better way to describe that, I think, from a physical standpoint. And then the follow-up question is, if that's true, how does that affect the cosmological constraints that you discussed later on warm
Yeah.
dark matter?
So that's a great question. I believe that maybe a way to say it is that the scatter between the thing you want me to use and the thing I'm actually using is actually small compared to the scatter between the stellar mass of the systems and the peak mass or the virial temperature. And because that scatter is larger, I don't actually think the modeling changes significantly. Now, so that's in the version of the model that I told you about, where what we're doing is essentially a statistical mapping to the peak mass. Once we start talking about actually modeling the histories, I think your point is more relevant and important. Once I actually want to model the full star formation history of the system, then I agree with you that the virial temperature is the more important and more relevant thing. So I don't know if you bought my answer.
Well,
I'm happy to
can I
talk about it more. Yeah.
Just a very quick follow-up. I mean, I think there's 2 points. One is the scatter, which is certainly important, but the second is systematic biases, right? Because if we're talking at reionization, redshift 6 or so, then the connection between the virial mass, the mass, and the temperature is off by almost an order of magnitude, and so that can be I think a really significant difference.
So I believe, and we should take this offline, and I'd love to discuss it more. But my short answer to your question is, in the version that I told you about, which is just really modeling the statistical galaxy halo connection, I don't think this difference matters at all. Once I start to talk about modeling the full star formation history, which we are now trying to do, I think the difference does matter, and it's an important point, and we should talk more about it.
I have Colin on my list. Are there other people who want to ask questions? Good, Colin. Colin, you're up.
Yeah, thanks for the great talk. I wanted to ask a little bit about the likelihood function for the dwarf galaxies. So I gather you're using both the number counts and the spatial distribution somehow, but what's the actual data vector and what's the form of the likelihood function that's used? Yeah,
good. So the real, well, actually, maybe I should show you this plot. The main thing that we're looking at is just the counts, but the counts in 2 regions of the sky. So we're looking at the DES counts and the pan-stars counts separately. And that part is important, that we look at both parts of it separately. There are other ways you could do this. You could really I think once we have the whole sky, it might make more sense to really model the region of the sky that potentially includes LMC satellites and the region that doesn't. That might even be more constraining. but that's basically what the likelihood looks like.
Or you could do a multipole expansion.
Yeah,
So it's like a cache statistic likelihood for these two separate number counts.
Exactly.
Two regions.
exactly.
Like,
Yeah.
I had two quick questions. One was on your simulations, I noticed you didn't have an M31, which seems like a common thing people go for. Did you play around with having it in an M31?
Yeah, so the short answer is not really, because it's much more computationally expensive. People have done that. I think for most of the things we've looked at, it isn't a very important effect, but it's important to check. It's important to check that and understand where it is an important effect and where it isn't. Yeah.
But you guys didn't look at that yet.
Right.
Right, okay. The other question was on Saga, do you actually mean that there was abundance of star forming, or do you mean there was a lack of quench?
Yeah, I was careful about my language because I think we have more confidence in one of those statements than we do in the other, but I think we now understand much better the answer to both of those questions. So in this original plot, what I think I would say is that both were true. Like the quenched fraction was low. For sure, we see those star-forming galaxies, so you can't argue with us about that. Those star-forming galaxies are there at higher numbers than they are in the Milky Way and the M31. So I think we can say that statement with very high confidence. We can also say separately that we did not see as many quenched systems. And that's a harder statement to make observationally. I think when in the published paper, we made that statement, we were pretty confident in it, but we had an error bar. I think we now have reduced that error bar significantly. So, you know, and we're still working on crossing those T's, dotting those I's, whatever. But yeah, I think the answer is really both. There are fewer quenched systems than there are in the Milky Way and more star-forming systems on average. And I think we now understand exactly what those limits are.
We have Vasily Balakarov online.
Hey, Vasily.
Hey, Risa, thanks for the cool talk. So you're saying that a quarter of satellites is predicted to come with the LMC, but if you take the actual observed currently satellites and you rewind their orbits and you see how many are consistent, then it turns out that only maybe 6, which is more like a 10th or fewer. So is there tension then in?
No, actually there isn't. We also get exactly that number, basically a 10th of the 60. So we get 6 of the 60. That was our result. When I said a quarter, I think we're actually predicting that there's more LMC, a larger fraction of the undetected systems are LMC associated. That's actually what I'm saying.
Okay, cool. So we're about to find them.
We're about to find them. Some of them should be in this region of the sky. Some of them should be farther out in the halo, but I think they should be there. I don't know exactly what that error bar is on a 10th to a quarter. So now that we actually have statistics, before we were doing this based on 2 realizations, we now can do it based on 25 realizations. And I think I'll have higher confidence in the answer I give you next time. But yeah, our current results are perfectly consistent with Gaia and totally independent in terms of the measurements. Like we find roughly 6 LMC associated satellites in these models.
Okay, cool.
From the spatial distribution, not from the proper motions.
Okay, interesting. And related question, you show that in your simulations, the LMC forms late, as it should, because there's strong observational evidence that it does form late.
Yeah.
So what happens with your simulated LMC? Why does it form late?
Yeah, so that's really interesting and cool. If you try to, we tried this explicitly, which is to choose simulations that had an LMC at the right position, but was accreted early, and it doesn't match the data. It doesn't match the data because if it was accreted early, it won't have as many of its satellites still hanging around in the region around it. And so that observational result on its own of the existence of all these guys in this part of the sky actually gives you that late accretion time. So it's yeah.
No, the accretion late, I understand. The formation of its stellar mass, right? Because I thought.
Formation of its stellar mass.
Yeah.
Yes. Okay. So I think that is, well, I would say it's a robust prediction that should happen late compared to, much larger mass systems. I think that statement about exactly the star formation histories of the LMCs in these models, I think are relatively weakly constrained from what we've done so far. And I wouldn't trust that result very much. I think we need to bring more data constraints into that before I really trust that result.
Okay, so you don't think it forms stars late? Because I mean, it's a massive system that has a clearly very lazy past, and then it kind of started forming stars late. We don't know why, but so I thought you said that your simulations kind of agree with that, and I thought you had.
They agree with that, but I think all I'm saying is that I think that's relatively unconstrained, and we should talk more about it. Yeah.
Cool. Thanks.
Okay, well, I think we should end it there. I can't stop myself from saying something philosophical, which is that, when we found planets around other stars, everything we thought about the solar system turned out to be false. And when we look at dwarf galaxies around other Milky Way analogs, it turns out the story is much more complex than we wanted to say. And it makes me wonder about cosmology as a whole. That was a lovely talk. Let's thank Risa.
Thank you.